Hello, everybody. It's a very nice to have all you guys here. So this is an event, a webinar from CINE, the Center of Innovation on New Energies. And this is an event where we put together researchers and students and the people attending from relating the questions to the two divisions, the dense energy carriers and the advanced energy storage. So I'll be more than happy to invite now Professor Anna to present about what is CINE and what is DEC. So to people from abroad to understand, to have a better understand what is the divisions, and then after Professor Rubens Maciel going to present what is the energy storage division. So please, Anna, go ahead.
Thank you, Hudson. So good morning. It's a pleasure to have all you here this morning. And maybe for some of you, it's going to be so afternoon. I would like to welcome also in name of my colleague here, Professor Rubens Maciel. So we're delighted to have you here today and tomorrow. But before starting my presentation, of course, I need to do some acknowledge some people here. So I would like to thank to all speakers for taking their time to present their work here to us, to our CINE community, especially during this pandemic time. I know that is a very troubled moment for everybody. We hope that we can gather as soon as possible in the near future. So thank you again for all the speakers. And of course, I need to thank the organizing committee, especially Professor Lúcia Mascaro from Federal University of São Carlos, and also Professor Hudson Zanin from here, from University of Campinas, and our Super Secretary, Mary, for all the work that is pending, putting all of this, all the talks and organizing this workshop. So thank you very much. So I hope that all the attendees here have a fruitful time, enjoy all the talks, and I hope that maybe some collaborations can start after this combined workshop. So I think, one more thing, I would like to thank also the knowledge, our education dissemination knowledge coordinator, the team of Professor Juarez Silva. I'd like to thank Jacqueline, Veronica, our journalists, for all their support to make this workshop happen. So I think with that, I think I finish here. Let me try to, okay, I'm going to share my screen, and please, because now I'm going to lose contact with, just a moment here. For some reason, I cannot pass my slides, Mary. Maybe someone is entering in the room. Okay. Can you see my screen now?
No.
No.
Okay, Zoom problems. Okay, it's morning, so okay, I think now let's try to do. Okay, I think now you can see my screen.
Yeah.
Yes, yes.
Okay.
Perfect.
So, okay, let me talk about the CINE. CINE is the Center for Innovation on New Energies, and CINE was conceived, think about the moment that we're actually passing through now. We're living a moment of in a transition in our economy, from economy based on the burning of fossil fuels to an economy that is based on the renewable energy. So that was the idea of building our center that is located here in Campinas. So CINE has as objectives in to develop what we call like better dense energy carriers, like for instance, think about the hydrogen, and also combine these dense energy carriers with novel technologies for energy storage conversion, like batteries and supercapacitors. We also have a division where we're trying to find better ways to convert methane, that is a methane, to chemical products. And also we have, the idea is also to use computational tools like machine learning, artificial intelligence to assist the development of the better materials and better systems. So with this in mind, so our FAPESP and Shell, our founding sponsors, so had this idea to conceive our center. Let's just some summary of what the CINE is today. So we have in total about 20 projects. What we are going to see here today is like half of these projects actually going on the dense energy carriers and advanced storage energy divisions. So I'm happy to say that we are in total now approaching 280 members between faculty, students, and postdocs. We had initial investment from $10 million from Shell. And also, if you take into account the investment from FAPESP and the co-investment from the university is more than $18 million. Again, I cannot pass my slides. Okay. So we have as leading research institutions, UNICAMP, here, University of Campinas, IPEM, that is the Institute for Nuclear Energy Research, and University of São Paulo, campus of São Carlos. So two divisions, the dense energy carriers divisions and the advanced storage divisions are here at the UNICAMP. So also have other key Brazilian research collaborations as Federal University of São Carlos, Federal University of ABC, University of São Paulo, Federal University of São Paulo, INPE, State University, I think, I cannot, UNESP, right? And the CTI. And also have very important collaborations with many universities and technology institutes overseas. So this is our team. Here we have on my side our deputy director from Shell, Camila Brandão, Professor Rubens Maciel, that is going to speak to you soon, that is principal investigator of advanced energy storage, Professor Juarez Silva from the University of São Paulo, that is the principal investigator of the computational material science and chemistry division, and Dr. Fábio Coral Fonseca from the Nuclear Energy Research Institute, IPEM, that is coordinator of the M2P methane to products division. Okay, I'm also very proud to present our International Advisory Board that is formed with many notable scientists, Professor Mike Toney, that is now in Boulder, Professor Ning, University of California in San Diego, Professor James Durant from Imperial College, Professor Hai Wei from Beijing Computational Science Research Center, Professor Prashant Kamat from the University of Notre Dame, and Professor Oswaldo Novaes de Oliveira Jr., o Chu, from here from University of São Paulo. So let me tell more about the program. So the Center for Innovation on New Energies is composed by 4 programs or 4 divisions. Besides the dense energy carriers and advanced energy storage divisions, we have the methane to product and the computational material science and chemistry program. Let me talk a little bit, because I'm also the principal coordinator of the dense energy carriers program. So let me talk a little bit more about our projects. Here we have 5 projects. So with the aim to develop more efficient and also more stable photoanodes and photocathodes, and for not only for water splitting reactions, but also think about CO2 photoreduction. What is important to say about the dense energy carriers division is that the core of our program are the in situ techniques. So in the last 2 years, we have been developing many and setting many in situ techniques, like for instance, in situ in situ infrared, in situ Raman, ellipsometry, and also in situ mass spectrometry. So all of these in situ techniques are really important because the other divisions are actually using our facilities. Here in Campinas, most of these in situ techniques are set here at Chemistry Institute in Campinas. So the idea is like that all the CINE community can actually participate and also take advantage of our facilities here for this in situ experiment. We also have a project on perovskite solar cells. I'm going to talk a little bit more about this project, not only to study the fundamental of this amazing semiconductor material, but also focusing on producing large area solar cells. So Professor Ruben is going to talk more in details about the project in the Advanced Energy Storage Program. So let me skip this. So let me just show you some numbers. I think it's important for the community to know, the CINE community to know the CINE. So we are now at the moment, this was our last survey. Let me show you here, let me go back. So we are approaching 280 members. So I'm very, very happy with this. Actually, I'm very happy with all the numbers. So between these 280 members, as you can see here, they are spread almost equally between the 4 divisions. So we have since scientific initiation students, like undergraduate students, master, PhD, and postdocs. So in total, we have 206 fellowships. As you can see here, most of our students, almost 47% are PhD students. And then we have about 20% of master students, 17% of undergraduate students that do what we call like initial scientific initiation, and about 16% of postdocs. Of course, that we are very alert here that we need to increase the number of postdocs. We have been talking to our sponsors, Shell and FAPESP, and I'm very happy to announce that recently you have the amendment for new postdocs scholarships. So stay tuned, because soon we hope to start to, we're going to start the call for these new postdocs fellowships. And I'm also very happy with the numbers. You can see here, in total have more than almost like 300 presentations in international and also in events here in Brazil. And also in terms of publications, CINE has published till now 215 publications, and we are 2 years, I think we have not completed 3 years yet. We're going to complete 3 years in August, so it's a really outstanding number for publications. See that the publications are growing. We don't have an idea what is supposed to happen in 2021. We hope that, I think it's going to be or a plateau, or maybe we see an increase in the number of publications, but I think we are doing a lot of, we're doing amazing work in publishing all of these publications, and many of these are, we can find in the front cover or even supplementary cover of any important journals from Royal Society, American Chemical Society, and Wiley, and so on. And also we have CINE is also because we have engineering schools here that is part of CINE, especially in the advanced energy storage. So we also have 2 patents claimed, and I think Professor from the advanced storage division, I think Professor Ruben is going to talk more about this. About these 2 patents, and also in our division, in the advanced energy carriers division, also we are working with some product development. That is for example, this is, I think I can play this video, by the way. Pablo just sent to me. So the group of Professor Pablo Fernandes here in Campinas, they developed this special electrochemical cell, especially designed to these in situ experiments. They were cover of CAN Electrochem, And also it's very interesting to say that this new electrochemical cell is not only, you can take this the cell also to the synchrotron. This is another important, investigation here in our division is also to collaborate with the synchrotron, especially for the in situ X-ray experiments. And also we have here another product in development. This is this perovskite solar models, and also I think I have a video here. As you can see, this is a 5x5 solar model that we are developing here at Unicamp. The idea is to go from this 5x5 to 20 by 20 centimeters, and we are talking to two Brazilian companies here to develop this large area modules. Is the one of them is the CINEDEC here in Brazil, located in Minas Gerais, and another company is the MG Grafeno, because the idea is to use this the graphene produced by MG Graphene as an electrode for contacting perovskite solar cells. So I think with this, I think I finished my part here. I ask to all the attendees here to follow us in our social media. We have channels and all the channels: Facebook, Twitter, YouTube, Instagram, and please visit our new website, www.cine.org.br. With this, I think I pass the words to Professor Rubens Maciel.
Thanks
and
very
I'll
much.
stop sharing.
Thanks very much, Anna. Before starting to share the screen, I would like to congratulate for the organization of this event. And I think you can see my screen now.
Not yet.
Not yet. So you are pressing to transition energy phase of our life, and the point that it's important to mention is that we don't have enough energy even in nowadays if you want to have energy for all the society, either for industrial application or for mobilities. Can you see my screen?
Yeah.
Yes, Rubens. Can you put in a presentation mode?
Yeah. So then just to pick up the idea, we have a selection of possible options to use our source of energy. And then the tendency is to go to do clean energy, worldwide speaking. And then wind and solar energy, together with biomass, appears to be the solution for the future, as you can see in this top screen, and the top figure of this screen. On the right-hand side, you see the oil profile that you are expecting to have. And then even, we don't have time to show here, but it's important to discuss with you that even that you can use all the oil available today. If the society needs energy as the developed countries are using for the older speaking population of the world, we don't have energy enough to that. So that means that not only we need renewable energy, but we need more energy. And again, biomass, wind and solar energy or source appears to be quite interesting. However, we are very far from that. If you look at this in the bottom part of this slide, we are even using too much renewable or not renewable energy, fossil-based energy. As the International Energy Agency is showing here, we have more or less 8% of the total energy generated in the world is from fossil base. And then, if you look into the scenario where biomass, we did a lot in the last years, especially in Brazil, that's the top country in the renewable energy. And then many advances you can see come in the left-hand side, since the development of new crops of microorganisms, carbon and the water footprint, a lot of things have been made in the biomass to become this one suitable solution. And in fact, it is nowadays with the ethanol program for 42 years in Brazil in biodiesel and so on, and sugarcane bagasse generate electricity. But we have to increase this energy matrix, and then this advanced energy storage system business play a quite important point, as Anna was mentioning. We have to try to repeat, I would say, the success of the balancing the carbon cycle in the industrial biotechnology approach that is use biomass. Try to understand the phenomena, then we may use the energy generated by the wind or aeolic energy and the wind energy, and then the solar energy. As you can see the right-hand side of this slide, usually the usage profile is not the same that the solar production is given to us. That means that you have to develop things to store this energy, either for industrial application, as I mentioned to you, or to mobility. And then this is with the AES, Advanced Energy Storage Program, comes with your 4 projects. One of them is development of high porous carbon-based materials for supercapacitors, and the characterization of supercapacitor in operation regime that is read by Professor Hudson Zanin, and the characterization of lithium oxygen batteries in situ dynamic operating conditions, and the project number 9, design and confection of new electrodes applied to lithium oxygen batteries, that's led by Professor Gustavo Gobeck. And I'm the PI of the division. And then it's quite important to use this opportunity to discuss with you, to bring a motivation why you're talking about supercapacitors and the batteries in the lithium oxygen context. If you look to this graph that's in the x-axis, you have energy density, and the y-axis, the output density, means if you look at the top side, is these supercapacitors, they are quite nice to deliver a high density energy, but they are not able to store it in a very large scale compared to the batteries that you can see in the bottom part of the right-hand side of this graph. However, the batteries are not able to supply the output density that you need. But for that, we're using these 2 approaches to bring all things together and improve time more the device that can provide enough energy for these several applications. Again, I will show you, I mentioned industrial application, housing application, that means store energy for large use people, or even for mobility, that means cars, buses, and in the trucks, and so on. And now we have to understand several mechanisms that are taking place in the system. Some of them is we are providing knowledge in this research to understand which species we want to control that are formed, and which species are not so good for our purpose. That means we have to go deeply in this understanding of the phenomena that are taking place in the system. And then we have several challenges, for instance, in the practical world, the loss of capacity due to the number of cycles that is showing the first graph on top left top side of this figure. And then the let's say the large of potential for charge and discharge time that may have, that means that we spend more energy than the device can store. And then this is a typical 3-phase boundary management problem that is not easy to solve. And then you have to use, as Professor Anna mentioned, in situ Raman measurements are quite nice, let's say, tools to understand the phenomena. And then we have go towards a solution. And that means to discover, to have knowledge of the phenomena and the new materials and the architecture that they are able to deliver to us what you want. That means to store more energy or large capacity, large density capacity, large output of energy. And then we have to go to novel electronic materials and their architectures, the combination of in situ and operando characterization techniques to understand the phenomena and bring this knowledge to the practical world. And then two large projects I would like to mention here that are taking place in our division is in situ operando, and then one having in situ and operando characterizations using Raman Spectroscopy, FTIR, and Snow nano FTIR, sequence-based X-ray techniques, and several partnerships with external institutions, including one that you are going to have today. It's a pleasure of presence of Professor Laurence from Liverpool University. And then we are also developing the virtual lithium-oxide battery environment development for mathematical modeling and the simulation environment for this kind of system, and to allow us to evaluate scenarios regarding stable batteries and supercapacitors and life cycle analysis. And then some quite interesting research have been made in novel materials and devices for supercaps. And then when you use carbon-based structures, that's a not easy work to do, to be done. So you have to understand how we are going to manufacture this kind of structures, to understand the different substrate that you have, the shapes, the amorphous, the crystallinity, and the effects of composites and the surface functionalizations. And then you have a lot of things to do, including electrode architecture and modified chemistry, using redox mediators, design of artificial small molecules, and put all these things together towards the objective that you want to increase the energy density, the energy output of the device. And then quite interesting work has been done also in the manufacturing pool cells. That's something that we need to do, and this reflects the science to technology. Woodson Running Group is working very hard to go to this approach. That means put in practice what you are learning in its research group. As was mentioned, we have climbed so far, in fact, 3. We are going to show here 2 intellectual property results as a result of these studies. One of them is regarding to the let's say the capacitance precision meter that was developed, a device able to measure the capacity with high degree of precision and accuracy. It's quite important. You can see in the YouTube how this is going to be, and then a crucial part of the research to development of supercaps. Another one is the development of electrochemical device for characterization of electrodes in dynamic operating machine, which appears to be a very simple idea, but it is not. It allows you to go to online in operando measurements that brings the idea of what's going on in practice, so that you can organize your mind, organize the activities, and mainly try to interfere in the process to obtain what you need. Again, I want to reinforce that we want to have high density and the high output of energy density devices. That's what we're looking for in this project. And then I would just like to finish with this very interesting image that I want to show you. We are a scientific group, and also science to technology, and also scientific scientific answers with, let's say, a very strong effort to understand the phenomenon and with a broader vision, looking around, look the practical application, but take into account the local restriction. Pay attention that the guys look through a hole to the wall, and then it's telling, I'm sure that's raining. That's a quite simplified analysis, and in the scientist is going top of step of the stair, and he's showing clearly that it's just a water tank leakage. So what these, I mean, let's to understand the phenomena, let's put in practice. That's what these two divisions are doing, and one of them to try to get high density energy molecules through the use of solar photovoltaic panels to absorb, to capture the energy of the sunlight, as this DEC division, as Professor Ana Flávia mentioned, and this division that is trying to store this energy. So in this, I give back the word to Professor Gustavo Dalbeck, give thanks to the CINEDEC teams, to Lucia Marconi for the organization, Hudson and Gustavo too, and to Mary for all the assistance. Even special thanks to Professor Laurence that's going to teach us, and his hosting of all of our students. And we'd like to thank you very much, all of you, and with us in these two quite interesting days. Give back the word to Gustavo Dalbeck. Thank you.
Thank you, Professor Rubens, for the presentation. We are just waiting Professor Hardwick to connect. We send him a link. Let's see if he can join the meeting.
Hello, Gustavo. It's Laurence Hardwick here.
Oh, hello, Professor Hardwick. Good to hear from you. So everything all right with your connection? And
yeah, yes, and yeah, I was in the wrong part of the room. So.
Oh, okay, no problem.
So I've been following the meeting.
Great.
At the beginning,
great.
So very interesting.
Great.
Thank you. Good.
So let me introduce Professor Hardwick. He's currently the director of the Stephenson Institute for Renewable Energy at the University of Liverpool in the UK, and a full professor in electrochemistry. He has a PhD in chemistry from the Swiss Federal Institute of Technology with masters from the University of Southampton. Before he joined the University of Liverpool, Professor Hardwick was also has worked at the Pochard Institute in Switzerland, the Berkeley National Lab in USA, and University of St. Andrews in UK. Professor Laurence is also the associate editor of many societies like Electrochemical Acta, the Royal Society of Chemistry, International Society of Electrochemistry, and the Electrochemical Society. As the author of many papers in high-impact journals, and also the reviewer for prestigious ones like Nature Communication, Nature Energy, Advanced Materials, Vante Chemie, among many others. And his main research area is focusing on the utilization and further development of advanced spectroscopic techniques in real-world systems like battery electrodes, such as Raman infrared to unravel the reaction mechanisms and structure of complex electrochemical interfaces. And we also have common student, Bianca. It's currently in the group of Professor Hardwick, developing some work related in our projects. And I'm very glad to welcome you to our workshop. And please feel free to welcome to our workshop. Thank you very much.
Okay, thank you, Gustavo, for the very kind welcome introduction. Yes, it's a great pleasure to be here this morning to talk to you all. So I thank you very much for the kind invitation. So I will I just there we go. So I shall begin my presentation. So hopefully you can all see the slide I've put up.
Yep, yeah, it's showing.
Perfect.
Thank
So
you.
yes, so I'm going to give an overview of some of the in situ vibrational spectroscopy we've been doing at Liverpool over the last past decade. As this is sort of a very international audience, I thought I'd just start my first slide just to highlight where in the UK Liverpool is. So we're in the northwest, northwest of England, and so it sits along a river Mersey, and so we have quite nice waterfront with historical buildings. This is sort of the image of the university central area, and if you don't know, Liverpool's what is unique in the UK is that unique as a city in the UK. It actually has two cathedrals, both so Catholic and a Protestant cathedral, and they sit sort of one end of one long street, and this is sort of mirrored by the two famous football clubs, which sort of sit either side of a park in North Liverpool as well. So to start off, I'd just like to acknowledge my research group who have done all the hard work of what I'm going to show today. So this is just the group as it was probably February last year. This photo was taken, and this is some of the work I'm also going to show from the past group, which has been captured in Lego form, and I believe I'm this character in the center here. And also as sort of acknowledged in the introduction, to acknowledge Bianca, who is a student who is from your institution, working here should be working here for a year, looking at in situ Raman microscopy on the lithium oxygen system. Okay, so what I wanted just to start with is just to define what we mean by in situ and operando, and the term operando is now becoming used much more frequently, and it seems these two terms are quite interchangeable. So I thought it's very useful when we're talking about spectroscopic techniques, whether it's done in situ or operando, what do we mean in particular. So if we look at the Latin description of in situ, it means on site or in position. So I would take that as an in situ experiment. We're looking using microscopy, for example, microscopy and measuring a certain position on an electrode interface, and maybe the system is not really as it would be for under realistic operation conditions. But recently there's this new term, or newish term, operando, and it comes from this Latin operando, which means working or operating. And so when we talk about operando spectroscopy, it's a measurement that is in place and under realistic operating conditions. So sort of under closer, say, electrochemical and geometric environment close to the application itself. So for example, if to do a operando, you do operando experiments using X-rays on a realistic lithium-ion jelly roll cell, for example. So in my talk, I will use both terms interchangeably, but it's just very useful to start with, sort of being very clear on what the differences are. So opticals diagnostics, particularly in batteries, and I just thank Jason Porter from Colorado School of Mines for inspiring this particular slide, as it shows very nicely sort of the increased number of publications where research groups have used optical techniques to look at to apply to battery research. And the reason for this is optical spectroscopy provides much needed information on all the components that are within the cell. And here's an example of a lithium-ion battery electrolyte containing ethylene carbonate and dimethyl carbonate and a lithium salt. You can get a huge amount of chemical information, such as the coordination. You can see how the peak shift changes due to the change of energies in the band that can be used to understand coordination, different intensities relating to the growth of appearance of different compounds, and the broadness, which can be related to, say, the crystallinity of certain materials. So you can get a huge amount of chemical information collected from Raman spectra whilst doing your measurements in battery cells. One thing that's certainly our group has benefited from immensely is that I mean, from our own efforts, and also commercially as well, and also learning from other research groups, is that we've greatly improved our optical cells for both in situ and operando studies. And this has been a huge benefit to sort of accelerate research, to be able to get very good quality spectra as we do the electrochemistry. So this next slide sort of highlights some of the areas that we're particularly focused on within our research group. And I'll mainly be talking on Raman spectroscopy, predominantly in this talk, but I just also wanted to highlight very briefly some of the research we're doing with in situ operando, in situ infrared spectroscopy. So we use the method that we use, or the geometry we use, this, it has a very huge sort of title. So we use attenuated total reflection surface enhanced infrared absorption spectroscopy, which has the acronym of ATR-CIRAS. So the sort of systems we're interested in this technique is really looking at changes of surface speciation at the actual electrode interface. And we use sort of nanostructured gold electrodes, which have been evaporated onto a prism, which is optically transparent to the infrared. And so we can enhance the local signal and see surface absorbates within this type of electrochemical cell. And we've used this pretty much exclusively looking at lithium oxygen or metal oxygen in environments to understand reaction mechanisms of alkali metal ions and oxygen that occur at the interface. So as I said, I won't be going into too much detail, but I just direct you to some of our recent publications to read further on the use of this technique, because you can really see monolayers of absorbed species, and it's a very powerful method. As I said, I'm going to focus really on Raman spectroscopy, both sort of conventional Raman spectroscopy, in situ Raman, looking really at the electrode, but also I'll now talk first really about the surface enhanced Raman spectroscopy that we use to really again see bands of species at the electrode surface, which have been absorbed at the electrode surface. So sort of really improving the sensitivity of Raman spectroscopy. And we do this with the more traditional surface enhanced Raman spectroscopy, where we electrochemically roughen a gold working electrode to give us a nanoscale roughness. And this gives us the surface plasmon to enhance the Raman signal. And so we have this sort of beaker cell here, and we have 3 electrode cell with a reference electrode and counter electrode. And here's our gold, nano-roughened gold. And so we can then mount this on our Raman spectrometer, do the electrochemistry, and then shine, as I'm doing my laser pointer here, and under potential control, collect the spectrum and see observed changes at the interface. So as I'll explain in a bit more detail, CIRS does have limitations. You're really, I mean, especially sort of limited to sort of gold interfaces and maybe just a few other materials. But what we've been using is this technique called shell isolated nanoparticles for enhanced Raman spectroscopy, which has this acronym of SHINERS. And so what we do, we have a nanoparticle of gold, about 50 nanometers, but we put a uniform silica shell completely around it. So we encapsulate this in a very thin silica shell, and it has still has a plasmon resonance, and we put these particles down, and we can put them down on any electrode surface. Just also to note, we have been doing some AFM, in situ AFM electrochemically to observe, say, in the formation of these sodium superoxide cubes for the sodium air battery. And we've been looking at certain more exotic types of spectroscopy in collaboration with national lab facilities. So the sort of next part of the talk, I'm going to focus on really on metal oxygen cells. So I thought it's just very useful. So these are for batteries, for energy storage systems. So this is our conventional lithium-ion battery. So here we have our negative electrode of the graphite and our positive electrode of the lithium copper oxide, and we have a non-aqueous lithium-ion conducting electrolyte. So we have it's an organic solvent the lithium salt's dissolved in, and the charges we can discharge the cell. So we have lithium ions stored within the graphite between these graphene sheets, and as we discharge, we can use an electron is transferred through an external circuit and can be used to do useful work as it then returns back into another layered material and stored between these cobalt oxygen. And so you can shuttle the lithium ions to and fro these intercalation reactions, and this is the method for charge storage. Now the lithium oxygen battery works slightly differently, is that some of the components are external. So here we have a sealed system. We have oxygen from the environment can diffuse into a porous electrode, there's a conductive scaffold which can provide electrons. We have again a non-aqueous electrolyte to provide lithium ions, and by stripping the lithium, we have an electron going through an external circuit doing useful work. We combine the three components and we grow ideally lithium peroxide in the lithium oxygen battery case, and this grows within this porous conductive network, and to some extent it can be reversed. And so the challenges are to try and get this chemistry to be much more reversible. And the motivation really behind people working on understanding and trying to develop metal oxygen batteries is really that their specific energy is at least the theoretical specific energy is almost an order of magnitude greater than the conventional lithium-ion technology. And so that's the sort of driver for seeing how good can we get in getting energy storage systems with high specific energies. So as just to note, so once we form this lithium peroxide, as I say, this can be oxidized to again release the oxygen. So you sort of have a breathing battery where you breathe in the oxygen to form the lithium peroxide, and then it breathes out again, and you can release the oxygen. So just a few notes on Raman spectroscopy. So it's a non-invasive technique. As I've mentioned, it can investigate chemical bonding on surface electrode species. We can use it, therefore, to really understand certain mechanistic features of our electrochemical system whilst under potential control. So the Raman effect is that we have a coherent light source, such as a laser, can excite our sample and then it excites an electron to a virtual energy state, and in most cases predominantly the most cases, that you have this elastically scattered light where no energy is lost, so it returns back to its original state. But a small percentage, or 1 in 10 to the 7 photons, can be inelastically scattered. And so this inelastically scattered light gives us our Raman signal. So the difference in the energies here relates to the chemical, the energies in the chemical bond. Now, for conventional Raman, even though this sounds very small, and I say the signal is weak, it's still strong enough for us to get very good Raman spectra of a whole host of different materials. But if we wanted to look at surface absorbates, sort of monolayers of materials on a surface, we really need to enhance the signal, because in this case, if we want to look at really small concentrations of species, the Raman effect, standard Raman effect, is way too weak. So surface enhanced spectroscopy has been around since the 1970s, when it was first reported. And you can enhance the Raman signal by, in very idealistic cases, up to 10 to the 11. So huge amounts of enhancement. However, SIRS is limited by the substrate material. So only certain materials can give a surface phonon to give the enhancement, such as these nanostructured surfaces, and there you're limited to silver, gold, or copper. So as an electrochemist, I'm maybe wanting to move, not really focus on these types of materials. I really want to understand other types of materials, particularly what's happening on carbon surfaces. If I want to do some very model studies, I'd want to use sort of single crystals, single crystal platinum, and understand the structure-surface relationships with respect to certain electrochemical reactions. So we need an alternative to SIRS to look at these other inactive electrode interfaces. And so we have as I introduced, this shell-isolated nanoparticles for enhanced Raman spectroscopy. So now we have our phonon source, surface phonon, locked within a silica shell, our gold nanoparticle. And so we can put our particles onto any electrode surface, and we can enhance the signal of certain components on that surface. And so it can be used on pretty much any electrode surface. It's optically inert, so these particles, they don't interfere with the Raman spectra, and we can get fairly usable signal enhancements up to 10 to the 5. And this is some of the challenges that we're working on, is developing certain particles which have a much greater pH stability. So this technique was first reported by the group of Tian in Xiamen in 2010, and now a number of research groups across the world are using this to look at certain number of different systems. And so this has been a sort of a major breakthrough within the last decade in terms of getting much more applicable sort of surface enhancement onto a number of different substrates beyond gold. So the shell that you put on your gold nanoparticle is extremely important. So you don't want it too thin, because then you run the risk of these pinholes. And so then all you would do is measure the Raman signal of any surface absorbates on the gold, which is not really what you want. You want to just measure on the electrode surface. But if you measure too thick, if you have a shell too thick, then you don't get very good signal enhancement. So there's a sort of sweet spot between 2 and 3 nanometers of thickness where you avoid pinholes, but it's thin enough to still give an appreciable signal enhancement. And so we have some transmission electron microscopy images here of some of these shells. And so what we've been working on is trying to improve the usability of this technique by using different shell coatings. work I'm going to show today is mainly using this silica shell. So we have our Shiner's particles here, and we've put this on a this is just an illustration. So we put pyridine down on planar gold, and so we can see our Shiner's particles here. And when we put pyridine, there's a band about just above 1,000 wave numbers, and it's from the absorbed pyridine. And so where we have these particles, there's a very nice correlation of the signal enhancement of this absorbed band of the pyridine. And in particular, we've used Shiner's to look at, for example, here in this example here of superoxide forming at the electrode interface, and we're comparing traditional CIRS here. So we have our gold oxygen band, which is growing as we reduce the oxygen and form this superoxide. So we have very nice correlation between the electrochemistry and the spectroscopy. And we've done this, repeated this again on planar gold and also many other different substrates, and seen the superoxide form. So we have this oxygen stretch of our superoxide, and we see this grow as the potential increases. And we've done a lot, just to sort of wrap up this section, we've done a lot of work looking on single crystals, particularly platinum single crystals, trying to really dig very deep into the reaction mechanisms of oxygen. And we've used Shiner's to look very carefully at sodium oxygen system and seen different reaction pathways on different orientations of platinum single crystals. And recently we've looked at calcium oxygen electrochemistry, and something very interesting happens with calcium is that initially when you cycle it, I don't know if you can see this little dash here, this is sort of the first cycle. It's very irreversible, but after cycling, you get a sort of calcium oxide layer on your electrode surface, which ends up trapping your tetrabutyl ammonium oxygen species, and it becomes trapped within this very thin layer on the electrode surface. And as it becomes trapped, it then is able to become then readily oxidized again. So after, say, 100 cycles, you can see that our red peak here has grown quite very significantly. And so we have this trapped interfacial redox within this system. And the blue trace is just the conventional signal you get when you don't have any calcium present at all. And so we used surface enhanced Raman spectroscopy to again look at and seeing what is to understand what is the electrochemically active species. And what we've seen is again that we again see this oxygen stretch of the superoxide and the gold oxygen stretch. So we can use Raman very nicely to identify some of the key species that are present on the interface. So just to finish off the talk, I just want to talk briefly about standard Raman microscopy. And we traditionally use this type of cell setup where we look at the electrode from the backside. So we usually have a current collector with a small aperture, and then we're able to then shine the laser through and then look at our active materials. So in this case, a graphite electrode. And so we were able to form a 2-electrode cell. So here we're getting a little bit more closer to say an operando condition. So we're really looking at a system as a sort of button, as a type of coin cell electrode, but we have optical access to that. And then we just mount it on the Raman spectrometer and a potentiostat. Now I want to sort of highlight some work we've done with electrochemical capacitors. Using that principle, we've done a lot of work on various different battery materials, but as I know this is an area also of interest, I thought I'd highlight it. So with electrochemical capacitor, the charge is stored. It's a physical process. In most cases, it's non-Faradaic, and charge is stored at an electrolyte interface. By separation of charge, we have a double layer. And so we can use Raman to look and examine this interface for both electrochemical capacitors and pseudocapacitors. So historically what I've done is look at trying to understand degradation mechanisms within supercapacitor electrolytes. And so this is a synthetic graphite. So this is not a graphite you'd actually use in a supercapacitor. So note the surface area is extremely small, but is really to sort of see what reactions are happening as you widen out potentials on very ordered or graphitic portions of the carbon you could be using. And both electrochemically and spectroscopically, you see very clearly there are some very nice redox peaks here, and this results of the tetraethyl ammonium that's been used in our electrolyte inserting in between the graphite layers. And so we see sort of classical splitting of the peaks, which is a result of the species being inserted between the graphite sheets. If we alternatively look at an activated carbon, so this is a carbon that you'd use in a supercapacitor, so it's got very high surface area. So you see also electrochemically, your response is very different to synthetic graphite, but also the spectra are very different. So the spectrum you measure for different types of carbons does vary depending on its crystallinity. And so you don't see a very nice splitting, but instead you see sort of subtle shifts and of these two main bands, the G and the D band of the carbon. And essentially the G band shift can be associated with a charge transfer onto the carbon bond, into the carbon sheet, and then the D band shift could be an indication of ion insertion into some of the ordered regions within this type of activated carbon. So you can use spectroscopy to sort of understand what is happening at this electrode interface. Finally, to highlight what we've also been looking at certain manganese oxides for pseudocapacitors, and this is just an example here of where we've used it very nicely to show how this manganese oxide of mainly Mn3O4 can then electrochemically converted into a manganese oxide, which gives much better pseudocapacitance by electrochemical cycling. And we here see how the capacitance improves as you cycle, and we've used the spectroscopy to look at how the different Raman bands vary between the as you cycle, and we can observe the change of this in the spectra. Okay, so my concluding remarks can be summarized as such. So vibrational spectroscopy can provide very detailed chemical information on electrode processes at the interface. So you can get information on the nature, the number of species present, the progress of reaction mechanisms, and also help understand certain degradation pathways. The rise of the availability of commercial cells for Raman and infrared or an FTIR even make even operando experiments much more accessible to the research community, which is a very, very good thing. And Raman in particular provides a very unique level of interfacial sensitivity, so particularly the surface enhanced Raman that I highlighted. And it's very, I mean, once if you have access to a spectrometer, which is expensive, but if your department is fortunate enough to have a Raman spectrometer for a reasonable budget of a few thousand, at least in pounds sterling, you can be able to set up these experiments and do this within the lab. So there's no need to go and use very expensive national facilities. You can do all this work within your own laboratory. And with that, I'd like to thank you for attention, and also just to highlight some of the more broader activity at Liverpool, where we're using computer and AI accelerated battery discovery and robotics to accelerate the discovery and characterization of new types of battery materials. And this is primarily within a large European project called BigMap, which has been funded under the Battery 2030. So with that, I thank you again for listening and welcome any questions.
Thank you very much, Professor Hardwick, for your very nice talk. We have one question here, actually. It's from Professor Pablo Fernandez. It's from the DEC division. So he's wanted to know if you face any reproducibility problems in the spectra when using shiners. The spectra is very reproducible. And another question is, how many days can you store the shiners without observing any changes in the performance?
Okay, yes, two very good questions. So, so reproducibility. So it's certainly not a one hit experiment and you move on to the next one. So generally, to ensure that the observation is genuine, we have to repeat the experiment at least 3 times to observe that the trend, you know, and maybe 2 different syntheses of Shiner's particles to confirm confirm the observation. So it's sort of a little bit more experimentally intense to ensure that you've got your reproducible results. But having said that, compared to, say, putting bare gold nanoparticles on, the frequency of artifacts is much lower using shiners than, say, using gold nanoparticles. So if you put bare gold nanoparticles on the surface, you tend to detect everything, even the smallest contamination in the system. And so this is then makes it much more experimentally challenging to sort of deconvolute your observations. So with shiners you get less enhancement, but also a lower amount of artifacts as well. And in the answer to the second question, so generally with the silica shiners, they're usually usable for a couple of weeks, and then you have to make a fresh batch. And this is part of what we've been working on for the last year and a bit, is looking at different types of coatings which can last for months rather than weeks. And so that's so we're hoping to sort of update very soon on some of the progress that we've been making in that particular area.
Thank you very much. Yeah, very important point there. We have some other questions here. So let me see if I can go in the order. It's from, it's changing here. Let me get here. It's from Professor Nagal. He's wanted to know what are the disadvantages and advantages of using FTIR instead of Raman in battery supercapacitor interfaces.
Okay, so we haven't done infrared on supercapacitor. We haven't used we haven't used in situ infrared spectroscopy for the capacitor interfaces. There is a limitation. I mean, the ATR Ceres is my favorite sort of infrared technique, but it does have this limitation. You can only look at the gold interface, and so we've really focused on looking at oxygen electrochemistry in non-aqueous systems, and also looking at how using different ionic liquids and see how the orientation of these or layering of these ionic liquids change under potential control. So there are some sort of compromises there. I think to get the interfacial sensitivity, you do need to use to have the sort of surface enhancement from the Ceres technique. So I think looking at carbons or more practical materials may be experimentally challenging.
We also have a question from Professor Woodson. Woodson, do you want to make it directly since you're in the...
Yeah, thank you very much, Gustavo. Laurence, thank you very much for the presentation. It was very nice, lovely. I always learn something, and I guess the students as well. So congratulations for the presentation. I have a simple question, and why you guys prefer to use, for example, the cell symmetry where you, for example, for supercapacitor, you if I understood right, you analyze the backside of the electrode, for example, in this kind of cells. Yeah.
Yep.
Because I'm asking this because of the electric fields you have in a supercapacitor. Yes. Yeah, go for it.
Yep. I mean, you're absolutely right. That's true. I mean, you really want to be looking at the front-facing part of the electrode. I think one of the challenges is to not have too thick of an electrolyte layer you're measuring through, which can interfere with some of the key bands that you're looking at. So this backside configuration is a messy compromise between being able to get the spectra. I would say the electrode is fairly thin. It's a porous electrode. So, and it's soaked in the electrolyte, and generally we don't see too much hysteresis between the electrochemical response and the spectroscopic response if we do scan slowly. But certainly if you're doing very high charge-discharge rates, particularly in supercapacitors, this configuration is probably not optimal. But if you just want to look at, as what we were looking at, sort of what happens to these materials under potential control, or do we see any sign of intercalation, then this is a reasonable experimental setup to take. It's, as I say, it is a porous electrode. It's not like a uniform barrier where you have to wait for some solid state diffusion to pass through. We really have micron particles or submicron particles where, you know, the interface you could argue that the electrode electrolyte interface even is at the backside.
Thank you very much.
Thank you, Professor. Oh, we have actually more questions are coming in. Not sure how much time do we have for all of them, but I'm just gonna go here as they are made. Thank you, Professor Hardwick, for the nice presentation. This is a question from Professor Leonardo. Please, can we give more details about inverse computational design of battery?
Sorry, could you repeat the question? Sorry.
To give more details about inverse computational design of battery. That was the question.
Yes. So, I can, I mean, within this, I can talk about our particular activity. So what we're working on at the moment is to sort of develop an autonomous route for coatings of active battery powders, and then sort of systematically and using automated analysis to develop different types of coatings. So this is sort of a new activity that's sort of started in the middle of the pandemic, and so this is an area we're very keen on in using some of the sort of unique facilities in Liverpool, such as the autonomous robotics. So I mean, there's a huge amount of activity going on with our other European partners in this project, and there is a website with increasing the amount of information. So if you've got a specific area of interest, please, I'd just direct you to that.
Thank you, Professor. Another question here, quickly. It's from Rafael. How could operando techniques could work in association complementary to computer simulations. What's your view over this?
So I would say I'm not sure about. I think certainly in terms of experimental design, if you had a particular observation that's within a model, you can design an experimental approach to follow some of these changes at the interface spectroscopically. In terms of what we've done, I didn't highlight it because I was conscious of time. So this isn't in any in situ measurements, but within this work here where we were designing electrolytes for metal air batteries, we did spectroscopy of a whole combinations of ternary electrolytes, and we worked very closely with modelers, and we had very nice correlation between the spectroscopy looking at the coordination environments of the lithium within these different solvents and the models. So all I can comment on is where we are. We're working at the moment, working with modelers on sort of static systems and understanding these local environments and then relating it to observed electrochemical properties.
Thank you. Thank you very much for answering all of them. Actually, we have a few more, but since we are actually, we exceeded the time actually for the next lecture. Let me ask if we can forward those questions to you, if that's okay.
Yes,
there's some more interesting questions here in the related to more specifics of the technique. So I think there might be very good ones. If is that okay?
That's but yes, and I'll endeavour to answer them today. So
thank you very much, Professor. Well, thank you very much for your acceptance of joining our workshop today and for the nice talk. And I'm guessing this is a very hot topic here, since there's many researchers and students working on different techniques related to spectroscopic measurements and also in situ and operando. So thank you again for your presentation.
Thank you, Gustavo. And yeah, thank you very much for
Gustavo. Let me just give last word to thank you, Professor Laurence, to receiving Bianca. She's very happy. Thanks very much for all the things that you have made for her. Thank you very much, Laurence.
That's no problem. It's a pleasure to have Bianca in the group. It's great. Thank you. Okay. Thank you very much for the questions.
Thank you, Professor. And so moving on to our next speaker, I guess, Hudson, are you going to make the introduction for Professor Renato?
Yeah, that will be my pleasure. So I'll be happy to present you guys Professor Renato Garcia de Freitas Sobrinho. He's a bachelor of chemistry from the Federal University of Uberlândia. He's a master on physical chemistry from the Federal University of São Carlos, where he also performed his PhD. Part of his PhD, he also performs in the School of Chemical Engineering and Advanced Materials, University of Newcastle. And he had been work with chemistry, physical chemistry, condensate state chemistry, and electrochemistry, which is we have a lot of interest in on this. So he had been work with us, and he's an expert on the electrified interface by complementary analysis, as Laurence has reported. For example, he do electrochemistry, and that will be the topic of his presentation today. So thank you, Renato, for being here, for finding time to be with us today, and he's all yours.
Thank you, Professor Hudson. Thank you very much indeed. Let me try to share my presentation down here. There's an option where the cursor became a pointer, isn't it? I don't know if you can see the cursor down here.
We can see.
Is it? Yeah, sure. So thank you very much indeed. Thank you, Professor Woodson, for the kind introduction. And today we're talking about electrochemistry, material science, and computational chemistry throughout energy conversion. I'm professor currently in Federal University of Mato Grosso, Chemistry Department. And I don't like to say that I'm head of computational materials laboratory, just part of them with the students, you know, as a professor. The student is the tough part of the team. And I'd like to thank all the CINE, the committee, the organizers, especially all the attendees. Last time I checked, 150 attendees. It's order higher than my physical chemistry and solid state chemistry classes, so it's a pleasure to talk about science for us. My wife used to say that as soon as I became older, I became a storyteller. Maybe she's right. It's a problem that happens with professor. We became older with so many stories. And I have a funny one when I was a PhD student with Professor Ernesto Laboratory. Professor Ernesto used to say, Renato, good science deserves a good coffee. And let's go to have a coffee and be CEO at UFSCar and have a pleasant time during that time. And when I was in Newcastle, Professor Paul Christensen and Andrew Hammond used to say, Renato, good science deserves a good tea and a proper amount of Georgia milk. And we have some brainstorms, fruitful discussions down there. And as soon as I became professor during this, one of the research meeting, first students, 19, 20 years old said, oh, Professor, all of them are wrong. To perform good science, we need good beer. And I said to him, don't you think you are too young to say this guy, too big boss like those one? No, Professor, I'm proud of myself, we need good beer. And now I know that all of them are wrong. Even Professor Ernesto, professor from UK, and my students are wrong. To perform good science, we need to perform good talking, and we need to talking about science. It doesn't matter what to drink or what to eat. It's need sometimes just right now, we have so many stamps and so many papers and so many bureaucracy and environmental, when we need a booking to stop and talk about science, it's a pleasure time. So we need just to help you have a fruitful time here. Let me introduce myself. I'm professor at UFMT, as I told you, in Mato Grosso state of Brazil, and Mato Grosso in Campi of Cuiabá. It's a pleasure to be a professor down here, especially for organic chemistry and biochemistry, our colleagues from biology, natural organic products, because Cuiabá, it's located, you see down here, in the middle of three massive biomes of Brazil. In Cuiabá, just in the city, just neighborhood of my home here, we have Amazonia, Pantanal, and Cerrado. So the flora and the fauna we have down here is quite different from all the other space. The flora here is quite different from Amazonia, it's different from the south Pantanal, and it's different from Cerrado. So from the leaf, they have some medicine for headache. From the middle, they have some medicine for sore throat. And from the roots, they have some medicine for, I don't know, cancer, for example. And so Cuiabá is very famous as well for the hot, to be a hot city, but we try to fix this problem with so many bunch of floods like APP, permanent protected area. There are some small biomes spread all around the city. So it's a very big city where, if you take a look, it's considered the greenest city of Brazil. It's a bird's eye view of our camps, just the exact earth and natural science down here. Unfortunately, we are on the pandemic time, but if not, my office is located close to this town here. And we also 50 kilometers almost close to Chapada dos Guimarães. That it's an amazing place, archaeological sites, and so many pleasant things to do down there. As soon as we finish this pandemic time, it will be a pleasure to invite all of you to have to perform some viva and the boarding evaluation of students. So NASA published this frame considering 2080 as the hottest year of since they start to record it. So this year we have on Scotland the COP26, which the code is already Unite the Road to Track on the Climate Change. And again, the Brazilian did the target in the spotlight of that one, because according to our government, we allow ourselves to devastate and burn Amazonia and 130,000 kilometers square. And where we are used to negative power, isn't it? 10 power minus 3, minus 5, minus 23, minus whatever. So 130,000 kilometers square. If you have an idea, the north of Ireland is 140,000 kilometers square. So we allow ourselves to devastate this area up to 2050 per year. So we can degrade 1 Ireland per year from now up to 2050. To solve and to fix this problem, we need to we need non-engineered materials. There are several of non-engineered materials which are able to convert energy, chemistry energy, into electric energy. So just here we have some example like fuel cells, solar cells, and the solar cell have a very massive bench of solar cells, water splitting, artificial leaf, dye solar cells, inorganic solar cells, supercapacitors, and lithium-ion as well as battery. During the previous time, we were using to study a lot fuel cells, which I consider as my first love, and solar cell as well. But now join the team of Professor Woodson, Professor Gustavo, Professor Renato as well. Our effort are target basically on supercapacitor and lithium-ion devices. And we have a computational laboratory. We have, for sure, we have potential starting in another colleague's laboratory, but the main students we use to do down here are mainly computational. So when we try to fix to help some electrochemistry colleagues, we use an electrochemical impedance and transmission line, structural properties like heat with filament, electronic structural properties, to study electronic properties, DFT and molecular dynamics, ab initio molecular dynamics as well, and some numerical modeling. Some of this computation we submit on Senapad. We have our workstation as well. We use GSAS for refill refinement, Gaussian, QuantExpress, MATLAB, and now we perform some routines in R, in our studio for machine learning, neural network as well. We have some here blocking the name of the Zoom. Well, Zoom have some tag here. I cannot see the title.
Professor Renato, for us, I guess it's purely fine.
Yeah, but Zoom have some tag here in the up part. I cannot see the title of the the title of the upper part of the slides. But anyway, when Professor Woodson invited me to talk today, he invited me to discuss some of transmission line. Well, transmission line, and today we have a joint workshop, isn't it, with density carrier, energy carrier, and advanced energy storage. Unless you work with single crystal, probably you have a porous electrode. I copy these figures from the CINE site, isn't it? So we have this one from the program one, this one from the program two, and we have two similarities in here. We have a porous electrode. When the more proper model, we can use impedance and transmission line. And also, as I will discuss further, we here the fractal dimension as well. So if you work from the program one or program two, probably you already have read something about impedance, and you have keep in touch with fitting some impedance as well with equivalent circuit of transmission line model. So I try to give some explanation about transmission line impedance, and soon after give some example of papers for our group from program 1, density carry, density energy carry, and advanced energy storage. Well, guys, I don't want to be a broken heart, but many of you give to De Levy as considered as the first guy who studied transmission line structure. But it's unfair because the first paper of De Levy is dated from 1963. But before, in 1960, Euler and co-workers have published a paper called this one in German, which we have only 93 citations. I checked in June 11, 2021, 93, and De Levy have 1,658. And the reason is quite simple. It's not German, isn't it? It's a German paper, and which translated is current distribution in porous electrodes. So here we have the flat porous electrode, we have the thickness, here we have some porous electrode with lamellus, isn't it? So it's possible to solve Fick equation like we are used to do in the first Fick law and second law, the porous electrode here in electrolyte. Ra is the ionic and B, A, electronic conductive, B is ionic conductive, and we have polarization as well. So we have the first transmission line suggested on the history. So we have here derivative equation of flux in tube divided by total flux is equal derivative of flux 1 divided by total flux. It's an oversimplification because according to Euler, they became equal, the electronic and ionic flux. As we know, it doesn't mean, it's not right, because we have here two terms, A cosine hyperbolic of L and B cosine hyperbolic of L as well, divided by A plus B, and according, I told you, A is electronic conductive and B ionic conductive. So it's 1960, a first model, but the brainstorm of transmission line had started just right now. Soon after, in 1963, De Levy suggested this study where you have cylindrical pores, and we have derivative equation of the Hond E, the Hond Z is equal minus current R dz. So we just put the minus to the left, so we have derivative, the Hond E, the Hond Z is IR equals 0. And derivative equation of current is the Hond I, the Hond C dz, it's minus capacitance, the Hond E, the Hond T dz. So if we put in the left, the Hond E dz plus capacity, the Hond T dt is equal 0. So if you have the derivative equation of the potential, the voltage, and the current, we can use the Kirchhoff law, isn't it, and solve. And the first transmission line suggested by De Levy is this one. So we have the Z here, Z plus dZ, we have the flux of current now here, E plus dE, and here we don't have a charge transfer process, as you see here, just the capacitance value. So De Levy in the first time in 1963, neglecting external electrode surface, which is a oversimplification, isn't it? The pores have a uniform distributed resistance and capacitance divided by L, the entire L. So they consider the uniform cylindrical pore. He neglected the curvature of the equipotent surface. And no electrode reaction, only capacitance effects. Also, the electrode materials present no resistance. So here we have a problem because we have a dependence of the wave function of the potential voltage we apply. We know that it decreases for inside the pores, isn't it? So as soon as we have higher inner surface pore, and we have as well the outer surface pore, the outer surface pore decreases, we have a surface flat. And as soon as we increase the area, we have a surface pore down there in the surface, just in the pore, the higher, the surface area there is quite higher. So if you take a look here, we have for a short period of time and high frequency, we are analyzing, studying the flat surface. However, for large time and low frequency, we have porous surface. As we see here, the impedance down there, the voltage and the current as well, and we have the impedance divided by frequency. So lower frequency, as soon as we decrease the frequency, increase the impedance. So we have, during this time, as a shorter time, the flat surface, and we increase, we have, like this figure, we have the decrease of this amplitude of the signal, and now we're mapping the porous voltage, the porous surface down there. And the part 2 of this similar paper in 1963, Delevi considered the first one, the main target was the penetration depth, isn't it? Now, in the mathematical description here, we can consider the diffusion process as often can be regarded as a process of plane diffusion. We have an element and we have a plane diffusion because the thickness of the diffusion layer is small compared to the radius of the curvature of the pores, isn't it? We have a plane diffusion, we have the curvature, and we have the double layer with a small layer thickness. So we have here the CINEDEC coordinate of the second Fick law to solve this problem. And now we have the transfer charge resistance as well. Now Delevi insert this term here. So we have the resistance, the voltage plus the current down there, and associated parallel, the capacitance and the resistance. And now, if you take a look here, we have the value of dt divided by r squared 2. And here in the I, we have the current related to cylinder and current divided by plane. If you take a look here in the profile of this figure, we see that this part are related to the shorter pore, the small pore here, and large convergence, because we have this series, the sum of n from 1 to infinity exponential minus beta n squared zeta. Zeta is this one, is this term here. Zeta is diffusion coefficient time divided by r, the radius squared. So here, this series converge quite faster. And here we have a low conversion of this term. So it was the first problem to compare large pores and small pores because the Bessel function during this paper doesn't converge and we have error. So it's quite harder to suggest the non-uniformity of the pores as well. And if you take a look here, we have the log of frequency in X, and here the phase angle. So if you take a look, we have 45 pore excitation from the pore here. As soon as the frequency increases, we have diffusion. As soon as frequency is increased a little bit more, we have reaction, electrode reaction. And here we have the double layer capacity. For sure, we have a broken electrode on the pore excitation down like this part. We have this term here quite larger, and we don't have diffusion on even electrode reaction. So we divide by here and have only double layer, as we can obtain with a Freitas on a Freitas reaction in a double layer reach the difference of a Freitas electrode and a supercapacitor, for example. And here again, Euler in 1964 published the paper, The Power Distribution in Cylindrical Porous Electrode. Here we have where ion species coming to here, and we have the radius of the porous down there. A is the porous, and we have applying potential voltage, the difference situated down here, plus positive voltage, and here the negative. So here we have the plot of the total current. It's considered as J, but it can be a charge as well. The total current and here, and the radius. So the Euler suggests a model with this transmission line where the current distribution for two cylindrical pores, the inner radius is 0.4 for both. For this curved one and this curved two, the inner pore was 0.4 centimeter, like here. And the outer pore are 0.6 centimeter, is the curved one. However, if we increase 0.6 centimeter up to 1.3, we have the change of the profile like obtained here. So for small pores, the transmission line works pretty well, like we see here in function 1. And in 2, when the outer radius increase from 0.6 up to 1.3, we have like, it looks like function power 2, but indeed we have this profile because the hyperbolic cotangent, as we see, the hyperbolic cotangent decrease, so we have the positive and negative values. So it already gives the insight of the morphology of power change and change the equivalent secret, the transmission line, and only for very small pores, as soon as we decrease the radius of this pore, we have the better fitting of this parameter. And in 1965, we have this paper, as I told you, the zoom is blocking here. We have the study of Delevi again from the, wait a minute, guys. Oh, thank you. The influence of surface roughness of solid surface on electrode measurement. So we have here, the LEV suggests a V growth. A V growth is an imperfection which we consider further as a pore. So a V growth is the pore like this one if the pure condition under Z axis. So if you have the pure condition under Z axis down there, we have two-dimensional solved problem. So we can change, we can become this model quite simple yet to one-dimensional model, resulting only this half of this V growth down here. If we change the Cronk size of half growth. The morphology of the pore was not the Delevi who discovered indeed. The first evidence of surface roughness was given to Borisova Yeschler in 1950. In 1950, only in 1960, 50 years later, that the Delevi could consider a mechanism like this one. So to use Kirchhoff as well, we have beta. Take a look at this beta. Beta is the angle of the pore. If you have a pore, we have a small beta. If you have a plane surface, we have beta like 90 degrees, normal angle like this one. So we have the derivative equation like E divided by impedance is equal E zeta each cosine beta. Sure. So we have this equation, the derivative of voltage is ER dz is E whole, the electroresistance cotangent beta dz dx. If you remember from the trigonometry, we have the cosine beta, cotangent beta of 90 degrees is equals 0. So the cosine of this beta, which we can see here to use Kirchhoff filter, the cosine of beta is 0. The cotangent of 90 degrees is 0, and the cosine of 90 degrees is 0. So as soon as the degree increases to 90, we have the flat surface. And we have as well this equation here, where we have the impedance of this pore can be considered as the electric resistance divided by tangent beta here, and the coefficient of mass, Zm, and we have two situations to study. As soon as beta is equal to 19 degrees, the beta goes to 90 degrees, the impedance goes to 0. If the impedance goes to 0, the theta goes to 90 degrees, so we have the flattest surface. If the beta goes to 0, we decrease the value of beta. If the beta goes to 0, the impedance goes to infinity. See, if the impedance goes to infinity, we have the degree, the theta. If you take a look in the LED paper, we have several tables. We have the degree goes to 45 degrees, like here. So we have the ideally porous the electrode, like we observe here. If you take a look, we have the log of frequency down here, and here we have the angle. So 90 degree here, and as soon as we decrease the rays, like suggested here, we goes to 45. Soon after, we have this paper of Shelda in 1975, who studied how the network fraction of power frequency dependence. Up to this time, we see that this fractional is not fractal, it's the fractional power frequency dependence, because the guys up to 1975 observed that we have the alpha values doesn't fit pretty well the impedance. If you take a look in the Nyquist impedance, isn't it? We don't have a semicircle. We call it semicircle, but indeed it's at the branch semicircle. So Sheldon suggests three models: the RC leader network, the simple one. The first are the parallel branched, like this one, when we don't have the capacitance observing species down there. And the first order series branched leader network here. We have a series of resistance, which could be the resistance to get inside of the pore or get outside of the pore, or the electrolyte resistance. Pay attention that all impedance of this transmission line is one channel, isn't it? And we have the capacitance down there with observing pores. So according to Sheldon, we have the pocket pores and the mound pores. The pores have the morphology, but morphology doesn't take into account here. Only the high frequency, but not the morphology. The first to suggest that one was Sheldon. So suppose that we have a porous, a pocket, with an electric field down here, like E, electric field line. We have a small vantage of flux of species in here. As soon as we increase the voltage, like here, if we increase the voltage, we increase the species. If we have a lot of species here, we have the Coulomb law, and we have the interaction of these species, and the electric field itself becomes the opposite side. So we have the flux of species who get inside the pores and they get outside the pores in a pocket one. However, in the mount, we have another terms, like the power of peaks. Like here, we have the inverted position of electric fields. We have the constant electric potential down there, as observed here. And we have the flux of species. So we have the electric field here, the flux of species down there, and the voltage, the constant voltage. For sure, it's the fitting of the voltage. It looks dissimilar here. So the guys observed that it depends on the morphology of the pore. So they suggested they have three regions: the A, where we have just a pictorial result like this observed here; the B, where is the suggested the model; and C, where we have a series of capacitance related to this one species inside the pores. The capacitance series related to, in parallel, a resistance. Whatever, the resistance of getting inside the pores, they get outside the pores, the attachment in the pores. During that time, it was not observed the blocking surface, not yet, like very common in organic polymers, but we have this here. So this electric field, the constant voltage observed here, it decreased from this time. If we have RC, we have a constant time, isn't it? And the authors observed that the top from the bottom here, the alpha values decrease 1 divided by 4 is one suggested morphology. 1 divided by 4, the time constant of RC considered as the time constant. Also, they suggested this equation, the propagation wavelength. So the propagation wavelength is RC. We have 2p divided by k, s squared, the 2g. G was get before from the German because G is the ground, so G is the electric voltage applied. The permissivity and frequency, and here for us physical chemists, make quite sense because we have K is the bihecular parameter. So as soon as we increase the bihecular parameter, we decrease the wavelength. So we now, for the first time, we inserted the bihecular parameter and the relation of S and P, and higher charge for cations, higher charge for anions, how these species make together, and increase for the conductance or the resistivity indeed of the electrolyte solution or not. So increase the bihecular parameter, we decrease that one. And we have here a brainstorm, a breakthrough, which was in 1975. Where this famous ingenious mathematical Bernier Mandelbrot suggests, I cannot read here, like I told you, because there's Zoom, but he suggested for the first time, he coined the term fractal. So is the book. I obtained that book, and the first paragraph of the chapter 1 is, why is the geometry often described as cold and dry? One reason lies on its inability to describe the shape of a cloud, a mountain, a coastal line, or a tree. Clouds are not sphere, mountains are not cones, and coastal lines are not circle, nor does line travel in a straight line. Yeah, guys, science is poetry as well. So as soon as Mandelbrot studied several kinds of fractal dimension, up from the cells from the brain, cells from the lungs, cells from the body, the coastline pictures, the leaves, several leaves. There's very similar, very systems we have spread for ourselves in the nature. He observed the dimension fractal and developed for some kinds of system, proper dimension, fractal dimension. So Kaiser, which is very famous, but for study the morphology of the pores, pay attention that up to here, only high frequency was discussed, isn't it? We are paying attention on high frequency because on the high frequency, we see the 45 increase from the transmission line pores. So many of you probably have high frequency and 45 slopes degrees and don't know how to use transmission line. And I unfortunately see that the guys goes there and just delete that part. So if you delete the transmission line part of 45 degree at high frequency, you have a equivalent circuit for sure. But unfortunately, we are making an underestimation of your system. We have a very fruitful system to study, and you just cut the part to use a wrong system as considered as transmission line. So the first to pay attention to middle frequency, because in the low frequency we have Barber, which was already discussed. It can be considered as transmission line as well, and was suggested by Kaiser. And this Kaiser, the name is Assessment of the Pore Structure Using Porous Electrode Impedance Measurement. So suppose we have a pore with this morphology. And according to the morphology, if you decrease or increase it like dx, just the size of this pore, the distance from this capacitance of the impedance increase as well. So we increase the impedance. This increase of the impedance of the constant time, if we increase the morphology of the system, like we have a transmission line using here. So if you take a look here, a very common one, a cylindrical pores, we observe like this one, 45 degrees and goes to up, down there. This morphology, like a lozenge, when we start to decrease the charge transfer like part here, the morphology of pore 3, like this one, a bubble, where a very small mount, remember this one, if we have a pocket of a mount one, and we have the impedance 4, let's consider here, and an open one, quite similar to number 1, if you take a look at the impedance profile in the next one for sure, 5 is pretty similar than 1. So Kaiser was the first to pay attention on this middle impedance and the morphology of the pores. So the Mahout in 1983 observed the fractal designs. The fractal was coined in 75. Only in 83, it was bring together to the impedance areas of study, isn't it? And we have here the Kaiser, the Mahout, we have the knee, which can be considered the gauge of measurement. The gauge of measurement can be considered if you have a knee like 0.5, we have a fractal dimension twice. As you see, if you take a look at half image, you see again. If you take a look at half image, you see the entire image again. If you have the fractal dimension, isn't it? So we can have any power 2, like a 2D system, and power 3 in a 3D system. And these curves are considered the von Koch curve, like this one, where D is the fractal dimension. So we have the fractal dimension power 1 divided by D means 1, divided by dt, where dt is the evolution of the time, isn't it? You have the J is the macroscopic flow across the macroscopic interface. As soon as the interface, the ions, cations, ions goes to the pores, and you have the K, a constant, delta X, the local driving force, which depends on the Hooke parameter as well, the bi-Hooke parameter, and dA, like here, we have the apparent fractal dimension. So for the first time, the von Koch curve was observed here. And this equation was used to insert in the alpha parameter in the impedance. So here we have, take a look here in this circle. This circle can be considered as the N. So every circle you see is the N repetition of this one. You have delta X of an entire circle, like the circle goes together and makes some curves and goes straight. And here we have a stochastic dimension of the lithium diffusion on the carbon porosity, like the very first slides I showed you from the carries energy and battery capacitors. And this guy stood fractal dimension and electrochemistry as well. So if you take a look here, we have a semicircle with a capacitance in parallel to a resistance, an X, and a perfect semicircle, X impedance. As soon as we increase the fractal dimension, like here, from this one to this one to this value, and increase one, we see that the CPE, we used to say CPE, goes to lower, isn't it? We have a parallel, it's a nomenclature, we have a parallel. So we have a small CPE, a high CPE, and a higher CPE, and the CPE here is increasing only the alpha value, the dimension fractal. And the middle, the center of the circle for the perfect capacitor is located on there, isn't it? A semicircle perfectly. And when inserted the fractal dimension, very small values of dimension fractal, we decrease to this value and up to very depressive semicircle, like this value here. And this guy studies very up to this time kind of system, and discovered that the dA, which apparent fractal dimension, most common in electrochemical system is 2 multiplied by fractal dimension divided by 2 minus d. So Pakowski-Forta, we will study this one. So everybody who study electrochemistry and impedance and try to fit in the parameters, who pay attention to the preset values, now try to use the fractal dimension. So Pakowski was a genius because he studied a lot fractal dimension and impedance dimension, and worked with one very, very bright single crystal. I work with a colleague of Pakowski personally, and he says the experiment of Pakowski was a week just to clean all the surface of the golden surface of the single crystal to perform a very massive clean surface and avoid all the boundary condition to obtain a very flat and very perfect smooth surface, but it's not possible. As you see, we have the attached electrolyte species and we have the dimension of fractal. So we have the frequency-dependent impedance of blocking electrode. So the admittance, which is considered the inverse of impedance, is conductive. The imaginary frequency power alpha. So the admittance is dependence of K, because the impedance here is quite different from the balance down there, is the quotient of the impedance for the admittance for initial values. It's equal K power alpha. And alpha, it's our alpha. Some authors consider as beta, but it's the CPE, the alpha of the CPE, responsible for the press of the semicircle. And the alpha is 1 divided by fractal dimension minus 1. So for this surface like this one, which we have a Koch surface, remember here, the von Koch, which in the paper is called a monster of the von Koch surface. So the monster of von Koch surface, we have several dimensions of fractal. A very smooth one, like 1.02, a more roughness one, 1.26, a very smoothed one, a very roughness one, 1.9. So the dimension like this one is a series of connected capacitance and impedance, because we have a branch of pores. We don't have a cylinder pore, isn't it? We have epsilon pores, we have the T pores, we have branch of pores, we have pores all connected itself. So we have this arrangement in Pakowski only in 1985 most of you students was even born during this time. Pakowski was the first to create this one and start to obtain the good results for the impedance fitting. So De Levy was a very studied guy, isn't it? He was the first one, was not the first one, as I told you, the Euler was the first one. So De Levy implemented one on the impedance values. So all the equation we have during that time. So look at the values. For alpha equal 1, which is pictorial for sure, we have a perfect semicircle, which is located here, 0.5. And the alpha decrease, and alpha 1 divided by dimension fractal minus 1, and the impedance values, the alpha from the Bruce equation further, and 0.9, 0.8, 0.7, 0.6, 0.5, and we have almost a depressed semicircle. And as soon as we decrease, if you take a look in De Levy in 1989, we see the 95 degrees down there, because if we decrease the pores, it became roughness, it became as rough, it became porous. So if you take a look in high frequency down there, you see the 45 degrees of impedance. And the Gassa studied nickel, like here. In the first moment, we have nickel in hydroxide 0.6 molar, isn't it? So we have a Tafel plot like there. We goes to 0 up to there, and I have a Tafel plot, observe it here, and they obtain the impedance. Like here, the corrosion of the nickel mesh, like nickel mesh here, and the corrosion soon after apply a anodic voltage, you have a very porosity like this one morphology. Previously, after. So we have this one, and minus 0.8, we have this profile, and 0.2 voltage, which is located down there, anodic current, we have this one, isn't it? So the Gassa was the first to separate the contribution of the pore resistance and the surface resistance as well, because we have here ZPL. ZPL is the impedance of a single cylinder pore, like that one, which has a dependence of hyperbolic cotangent. You have the zero, the impedance of Z0 is the specific impedance per unit area, is the parallel impedance for a capacitor like handles, isn't it? We have the resistance in parallel with a capacitor. The ZP is the overall impedance, it's the most important equation, because according to Gassa, the overall impedance of the pore is the electric impedance, and this one, the pore of a cylindrical, the impedance of a cylindrical pore. And we can, several equations of sure, we can observe it here, but the Gassa was, the main result obtained down here was the one. The total impedance, the overall impedance is the electronic impedance plus the impedance of the cylindrical pores divided by N, where N is the number of pores we have down there. Soon after, in 1943, 1950, 1993, Pasch suggested the microhomogeneous porous electrode, because Pasch observed that we need to insert another term here, call it hindrance. If you take a look here, we have the electrolyte, isn't it? So we have electric field 2. We have a constant voltage here, electric voltage Phi1, constant. You have the increase of X plus dx, and we have the contact. So Gassa divide the electrolyte ionic current here, like we have the R2, and the solid phase electronic current. So we have the electronic current part of this transmission line, and the ionic current, which makes sense, isn't it? And electronic current is faster, order faster than ionic current. Ionic of an ion getting inside from the pore, it cannot compare for the electronic structure like in nanotubes, we have ballistic conduction like this one. So these models were further generalized by including an arbitrary time delay called hindrance. This term here is called hindrance. All this part here is hindrance like G of the charge transporters process of the pore surface. You have two hindrance processes considered here for Pasch, namely control of the charge transfer by finite diffusion. We have a finite diffusion of a species getting inside from the pore, and the formation of the pseudocapacitance. As soon as this species goes to inside the pore and attach it to the surface, we have the charge storage on a molecular scale. So here we have the transmission line. The hindrance term is this one. The rate equation of I is the hindrance, this part of here. And the equation is this one, G. G, the hindrance effect of charge transfer, is function of electrovoltage. The integrate of minus infinity plus infinity, G, the charge transfer. And we have the kernel, like here, Y, like T minus T line, potential or voltage here, X on dt line. So if you take a look, we have T and T line. It's quite small, but we have T and T line. X, function of T line, and here T line as well. Because as a result, the Faraday current was given dependence of T. It depends not on the instantaneous overpotential at the present moment, but also on the overpotential of the early times. The T line, we can consider T line lower than T, because we have an overpotential. The ion, the cation anion, depends on the voltage applied to the surface, goes to the pores attached. So the overvoltage is now have another value. So we have a two dependence, a dependence along the time. It was suggested by Paich in 1993. And finally, Professor Ernesto Pereira and Bisquet suggested using a double line channel, like this one, a transmission line channel, where we have a counter electrode, a working electrode, like this one, a solid surface, a porous like C1 for ionic diffusion, and electronic diffusion, situ. Zeta was the interface, and you have a couple of equations here. And if you use diffusion response function, we have the current values have a dependence of dA. If dA is the Einstein relation, so if you have a pore and we have a species goes to get inside and attached to the pore, we have the diffusion of this species, and all these mechanical statistics was considered here. And we have now a double line, for example, like here, R1, which can be considered like this one, the ionic diffusion. You have two parallel resistance and a capacitance of adsorbing molecule or some species attached here or some electric position get inside in the tube, and the capacitance of this part here. For sure, we have another part which is not shown here, the solution resistance, that is part here. So as soon as we increase the resistance, R1, for example, 10 power 4, 10 power 5, and 0, we have the morphology of Nyquist change. Take a look here. And the capacitance as well, 10 power minus 2, 10 power minus 3, 10 power minus 4, we have this decreasing. So this transmission line was very useful during this time to study polymer transport of polyaniline, PT, 350, and so we have the conduction, which the polymer can be considered for titanium oxide as well, ballistic transport, and the species who get inside and outside of the surface. And finally, Biscay and Gratzel in 2006 published this one with a transmission line with 3 channels, like here. Suppose we have electron energy, for sure. We have 2 bands, isn't it? Conduction band and valence band. And we have an oxide, depending on the engineer of the band, the dye current can inject on the semiconductor, or it can absorb and electron can recombinate on this part here. So Gratzel and Bisquet suggested titanium oxide in a dye, which one we have an oxide which injected on the dye. And the level of the conduction band and valence band was pretty different. So they considered 3 lines in this case. One line from this one, and from electrical one. So we have the resistance, this line here, another part related here, and this part here. So we have the impedance, so transmission line here, and 3 line channels like this one, 3 line, and 3 lines. So we have observed species, transmission, charge transfer here, another charge transfer process here. So If you take a look here, it looks like some circle, isn't it? But in high frequency, we have a 45 degrees, which related to the transport of the porals. So this oxide, the semiconductor, covered by some organic species, some dye species. And I could bring several kinds of systems to study, but if you have a joint and an energy carrier and an energy conversion system, I think the titanium oxide is very fruitful for discussion because it can work as a template for the battery or supercapacitor, or on the dark, titanium oxide is a dielectric, isn't it? But if you put light on that, it's a semiconductor. So it's a very massive kind of semiconductor used. In Brazil have several mines of titanium oxide, titanium indeed, the mineral. And the process to obtain titanium oxide is quite simple. If you put the titanium foil in an anode and the cathode, the platinum in the cathode here, and apply a voltage, suppose 40 volts, 60 volts. I mean, if you have 1 or 2 volts, we have an electric field strength up to 10⁻⁹ volts per meter. So can you imagine apply 60 volts or 90 volts to obtain titanium oxide? So we have applied to force the oxygen get inside to the surface, and titanium oxide in the middle of fluoride species is soluble. Fluoride of titanium is a soluble species. So we have initially the decrease of current, like here, because we have a passivating surface decreasing, like this part here. We align the electric field. As soon as we started to corrosion to obtain the tubes, the initial steps of the tubes, we have the increase of the current up to obtain this part here, the alignment and spherical impediment of the voltage of the tubes itself. And we have a package of tubes where you get inside of each tube of this one. If nanotube can be considered as a battery itself or a channel of a supercapacitor as well. And we have a decrease of the current constantly as soon as we increase the titanium oxide nanotube thick layer. And we have for sure the water splitting here and a gradient of voltage. As soon as the potential used to obtain the nanotube, larger is the tube. As soon as we decrease to a small volume, the tube became small. Large nanotube anodization values, we have the thicker nanotube. So we can obtain titanium oxide nanotubes from nanometers, few nanometers, up to micrometers nanotube. And we have the gradient of this one. It's a finite element method used to study. So here the guys use it to voltage one larger, like here, and take a short to a small voltage like this one. And we have a split of this part here. It's very interesting, very useful for batteries and supercapacitor because we have the blocked surface. If you block the surface, we can make the extraction, the lithium or the sulfate or depends on whatever, the counter ion most difficult. So we increase the time, the time of discharge like this here. If you take a look, all this part here was a pulse of voltage, and we can obtain process like this one and put the mesh together, and became quite difficult to lithium get inside and get outside from the surface. So here I bring some specific capacitance. Why titanium nanotubes? For specific capacity, million per hour means one. You have, since from 3 kinds of batteries nowadays, isn't it? Lithium ion, sodium ion, and 3 electrons. We convert 3 electrons with increased the efficiency, isn't it? Aluminum battery as well. So we have titanium anatase, this part 50 to 100. We have titanium oxide with carbon doped, increased to up to 250. We have for sodium amorphous titanium doped with carbon, sulfur doped with just put some lithium ion and sulfur species, with phosphor as well, the bulky ion. The amorphous titanium oxide for aluminum is this one. So it's 2019 is very updated paper. So it's a very common template for battery energy storage conversion and for energy conversion for solar cells and water splitting as well. So in this paper, we studied the effect of insert a defect, because as we know, as soon as we have a photon with energy higher than the band gap, we have the exciton formation, we have electron hole diffusion, and we have the recombination of electron hole. But for sure, we can consider as a ballistic conduction, but if we insert defects purposely, intentionally, defects of this one. So in this paper, we apply titanium anodization and a constant voltage of 60 volts and a pulsed one, 60 and 40, 60 voltage, 40 voltage, 60 voltage, 40 voltage. So we obtain like this one, the guys used to say a bamboo titanium oxide nanotubes, where each of the segment can be considered as a defect, isn't it? So if you have an electron conduction, in this part, we have a segment of defect. And deposit inside zinc sulfate using microwave hydrothermal method. So there's the chamber, the reactor. We put the titanium nanotube oxide down there with a species responsible to convert sulfur and zinc and put in a hydrothermal, and you obtain these photovalues. Here we have the current and the energy. If you have the inter photo conversion efficiency, we have two kind of system. For example, constant voltage and pulsed voltage without quantum dots, zinc sulfate quantum dots, and we have titanium nanotube with zinc sulfate quantum dots, constant voltage and pulsed voltage. Take a look here at C. We have the quantum dots, constant voltage higher, 16, than pulsed voltage, like down there, that one. For without quantum dots as well, we have the A, constant voltage, increase compared for that one, pulsed voltage, isn't it? And we fitted this value using an envelope function like this one. This envelope function was further proposed by Alan Higa, the group of Professor Alan Higa, when they used to study conduction polymer, because as we see, the Gaussian function is not symmetry, isn't it? We have the asymmetry of this envelope function. So this asymmetry, according to Professor Alan Higa, was related to the branches of the polymers. So we have orthomethod parapolymers. According to the polymerization, we have more branches, polymers, or more aligned polymers. So the envelope function will give us the asymmetry of this system. So if you take a look here, the asymmetry, this envelope function have a term called T0, this one, and it's from constant voltage 0.21 and from pulsed voltage, where we call it bamboo nanotubes, is 0.24. For quantum dots zinc sulfate, like constant voltage 0.25 and 0.26 for pulsed voltage as well. So we observe not only the increase of photocurrent efficiency for quantum dots, but we observe as well the efficiency of the envelope function to fit in these values. And a proper system for a proper model, isn't it? Because we have a nanotube like the one with a constant voltage, with a pictorial representation like the one, two-channel transmission line model, and this one for pulsed voltage. So we have the transport resistance, the capacitance of double layer, charge transfer resistance, and accumulate of charge on these parts here to fit the resistance. We call it the channel resistance and the capacitance of channel. So for sure, with constant voltage and quantum dots, we decrease the charge transfer resistance, as we observe here, the lower values, C, titanium nanotube oxide, zinc sulfate quantum dots, constant voltage. We also observed here the exciton, the screening the by length. So I'm not showing here, but screening the by length was larger for the constant voltage value compared to pulsed one, which are related to electron hole mobility and recombination. The charge transfer decrease. Here we have a transmission line, as we just discussing in the beginning, the 45 degrees, and the transfer, the resistance of the channel increased for 45, 48, 85 in this case. And we observed here the diffraction, and we performed on the heat field refinement. So as soon as we obtain the heat field refinement, we obtain the CI file, crystallographic information file. So it's possible to converted that one, that electrode in the unit cell, isn't it? So we have the anaphase, titanium oxide like this one, and we push this oxygen here to induce a defect, like very discussed of the band gap is a function of defect. Professor Elson Longo used to have several couple of models as well for this one. So we put a vector, let's say here, to displacement this oxygen, and we have this model here, perfect titanium oxide, disordered oxygen, and we simulate a titanium oxide nanotube properly. So we have a band structure here with an indirect band gap, 3.7, almost 3.6, indirect with Xc to gamma band gap. For the perfect one, as soon as we increase the shift the oxygen position, we decrease the band gap values, conduction, the valence band and the conduction band 3.09 down there, indirect band gap as well, gamma C. And for titanium nanotube is the Bruges equation are considered that the gap values a function of the radius of the ballistic conduction for sure. So we obtain the N gamma values lower, 2.49, indirect band gap as well for this third system with the titanium nanotube, the system. Also, we observe the PDOS, where you can see here the higher oxygen contribution down there on the valence band. On the conduction band, higher titanium contribution, like in gray down here. In green, for the perfect one, for the oxygen displacement, we observed in green the oxygen, higher contribution of density of states in here, and the blue one, the titanium increased the contribution for the conduction band, valence band, conduction band. And from the nanotubes properly, we have the, again, oxygen contribution, higher contribution of titanium, 2.9 band gap, and the map of charge. For a perfect one, we have a map of charge on this 101, I think, 101, because 101 was observed during the Heathrow refinement down there. And 101, a shift of displacement down here, we observe a decrease of the charge, the electronic displacement here. And for sure, even for 901, but another arrangement, we observe another kind of charge map for titanium nanotubes in here. And Professor Hubbard, published in 2009, using finite element method, using console, they solved this differential equation where we have the flux of current is minus concentration of mobility, the gradient of flux, hyperbolic function of this part, and they observing the flat parts of the current as observed here, and here the stress and the diffusion, the normal velocity of diffusion of these pulses. I cannot read in this part because it doesn't allow me, but it was aluminum oxide. But it's an oxide, and the phenomenon of nanopores or nanotube of anodization is quite similar. So we observe that we have a stress down there. So we read this paper and we thought, oh, for sure, they observed the stress, and he induced the stress because you see here, the stress is quite higher here and not here. We need I must spotlight here that it's a dielectric oxide, isn't it? So the electric field is quite higher here than here. Aluminum is a conductor, but aluminum oxide is a dielectric, like titanium. Titanium is a conductor, but titanium oxide is dielectric. So as soon as we read this paper, we induce stress as well in titanium oxide nanotubes, applying different voltage values, and change the percentage of ionic liquid, which was the precursor of fluoride to obtain fluoride species. So we visit two systems, 40 degrees, 1% ionic liquid, 40 voltage, 1% ionic liquid and 5%, 80 voltage, 1% and 5%. So we have porous nanotube with 20 nanometers, 36 nanometers, 97 nanometers, and 164 nanometers of diameter. We obtain the titanium oxide nanotubes with heat refinement, for sure, and we obtain the all structure parameters, and you obtain here 0.10 10⁻⁴ millivolts per second, the voltammetry, and we observe the oxidation, reduction of lithium, the charge, discharge of this party here as well. And we constructed this plot, which we observe here. We have anodic charge, and down there, the cathodic charge, isn't it? So we have a very reversible system, like here, anodic divided by cathodic equal 1, when we have the crystal size like this value, 34, obtained by heat flow. So 34 nanometers lead us to this part here, which is small lattice strain, which is nanotube considered here. As soon as we decrease the diameter of the nanotubes, we observe that crystal size, the crystal size decreases as well for 34 ohms to 22, like here, and this stress of border of the grains of conduction, the border increasing. As a result, we increase the lattice strain from 0.35 up to 0.7. So if we increase the lattice strain, so we can tune the effect of the lattice strain, and as a result, we can tune the reversible system of the ability to lithium get inside the nanotube and get outside the nanotube, because here the charge of cathode divided by anode values is 1.6. So again, some structural and electronic properties which result in some modifications in electronic properties like energy conversion or storage in this case. In this paper here, we made again titanium anodization, obtained 2 titanium nanotubes, and we electrodeposited cadmium selenide because the bands of cadmium selenide is quite different. For titanium nanotubes, and as all of us know, is almost 3.2, the band gap values, isn't it? But cadmium selenide not, is quite shorter. So we have a band gap, a position of band, very special, like this one. So the intent of this part during the time was the cadmium selenide absorb the species and injecting directly in conduction band of titanium oxide. Okay, but how we perform this one? We need to electrodeposit cadmium selenide inside the nanotubes, isn't it? But as soon as we obtain the titanium oxide, it's amorphous. As I told you, we need to insert that one in an electrochemical cell, apply an electric field with fluoride the species, and we have amorphous. Depend on the temperature calcinated, we obtain an natase, ruthenium, and mixed part of natase, ruthenium, brookite, and whatever. And we need to electrodeposit cadmium selenide inside the nanotubes. And the question was, when do that one? Previously, thermal treatment, or later thermal treatment, like that one. Previously, we obtained the titanium nanotube, calcinated, electrodeposit cadmium selenide, or later, we obtained that one, calcinate, and soon after, electrodeposition cadmium selenide. And we perform as well heat refinement, G6, PV, TCC, GZ, the function, the Cox-Haas function to obtain the heat field. And the most important part of that one is the tube, for sure. Take a look here. The tube is opened. You see here, the tube is opened. Even for that one, previously calcinated, or later, we electrodeposit and calcinate that one. And it's opened. It's not quite simple. Oh, come on, professor, it's quite simple. You just put I do that one in physical chemistry experimental. During the undergraduate, I put the electrode, apply electric field, and the cations goes there and deposit them on the surface, but not. If you remember, titanium is a conductor, but titanium oxide not. Titanium oxide is a semiconductor, it's a bright and very, very, very special kind of materials. But in the dark condition, it's a dielectric. And deposit on titanium is one thing. Deposit titanium oxide on the dark condition is quite different, because titanium, as I told, is a conductor, but titanium oxide is a dielectric, it's an oxide. So we have a decreasing of the voltage. During the long time, group of Professor Ernesto was trying to deposit cobalt inside the aluminum. And what the several groups of spreader would obtain, the blockage of the surface, because the electric field is higher on the top of the tube than from the bottom. As we observe and studying transmission line, the impedance is quite higher in the top of there, we have the small values in the bottom of the tube. So during the electric deposition, strength field is quite high in the mouth of the tube. So we blocked the surface and the tube became empty, which was not the case. We would like to deposit everywhere. So we obtained the previously thermal treatment, later thermal treatment, heat field refinement again, and observe the A parameter, C parameter, Lex parameter, isn't it? And a preferred crystal orientation on C-axis. As we observe it here, just observing here, if you know crystallography, you know that it's oriented, preferred oriented, because we don't have the small decreasing like sine function like here in this part of this one. So we're using, I cannot read it here, but probably is writing Mark Dollars here, use the Mark Dollars approach to obtain the preferred orientation. And the crystal size is 297, previously, later 360, and the lattice strain 0.4, 0.5, the rate for refinement. And Professor Ernesto performed heat field finite element method. So we have the anode, the cathode, this part, and we have finite element method to observe how decreasing, how is the function of the voltage on the tube. Here's the mesh of the electron line part there, the tube, and the electric field here. Is the thickness, I will pleasure to discuss all this equation, the thickness of the thickness of the film, the Butler-Vollmer, the thick first, second law, but the most important is this part here. If you take a look in this ISO line is 0.9, isn't it? The diffusion profile, 0.9, 0.99, 0.96, 0.98, 0.8, 0.7, 0.6, 0.5, 0.4. So as soon as it goes to the tube, get inside of the nanotube, the diffusion profile decreases. As a result, it is a result of decrease of the voltage drop. If you take a look in this part here, is the voltage, here's the relative voltage, the drop of the template down there. So if you have a high diffusion profile like here, we have a high voltage value like this part 3, voltage, the rate of voltage is 1. So here, as soon as we go to the top of the tube, the voltage decreases to 2. So we have the half value of the tube, half value of the voltage applied initially. And if you decrease a little bit more, the values here in the inner part of the tube down here, 1 is getting sight on the tube, the voltage decreased to 10 power minus 4. So we have relative voltage, so 10 power 4 outside of the tube from the electrolyte part up to 10 power minus 4 getting sight of the nanotube. So how to solve this problem? Use a very easy approach, the second Fickle law. Why? If you have two systems, the previously thermal treatment and later thermal treatment, and we applied anodic pulse and cathodic pulse, anodic pulse, cathodic pulse. So we smushing, we scuttling the part of the species go inside to the tube. As soon as we apply anodic pulse, we deposited selenide, and we applied the cathodic one with deposit of cadmium, and anodic and cathodic, anodic and cathodic, anodic and cathodic, and we goes to cadmium get inside, selenide get inside, cadmium get inside, selenide get inside, and alternating short pulse, so we don't block in the surface, and we deposit overall the nanotube. We use the Bisquet, the Professor Juan Bisquet approach to studying the open voltage pulse voltage decay. Why this one? But if you take a look here, the open voltage decay is, if your open voltage is illuminated, we have all electrons considering the top band, isn't it? The conduction band. And if we turn off the conduction band, the electrons with combination to the valence band. So the lifetime here, this part is considering a higher lifetime, and here we have lower lifetime. So the lifetime is higher for previous thermal treatment compared to later thermal treatment. That one. And also we observed, we made some quantum special computation. We have the bond circles with more chronopini. So we have a broadband here. So a broadband, a derivative of the broadband, give us the effective electron hole mass. So previously, thermal treatment, later, we observe the decrease of the band gap as well, and the mobility. It's for the mobility of the previously, for electron mobility is higher than later, 0.14, 0.32. Here for hole as well, the mobility of hole is higher than electron for sure, and is lower from the previous compared to later, 0.65. Also here, a higher contribution of oxygen and a higher contribution of titanium. I don't know what about my time, but I think
yes, that's I want to say. Can you go for conclusions because of measure force? Can you hear me? Can you go for conclusions because
yeah,
of
for
the,
sure. For sure.
Yeah, it's very good. Just because of the time.
Yeah, for sure. So it's a paper we published with joined the Professor Hudson, where we studied the dynamic of interface. Like here, we perform quantum espresso computation to see how nickel oxide goes to nickel hydroxide. Two Nobel Prize was inspired us to study the oscillation of the methyl platinum and platinum rhodioplatinum as well, with a tough group on this study, Professor Nagal, Professor Milton Varela. So we perform wavelet transform, observed higher drift for platinum compared to that one. We observed the shift of the band center for cobalt, when we put the cobalt, get inside the platinum compared to platinum and the multilayer. If you take a look at iridium and platinum, it's quite similar, but the idealized D band, the overlap of the matrix, the center band and the Buch-Wigner site is quite different. It's enough to change the stress. So as soon as we cover the middle layer, the bottom layer of iridium, we decrease the band center of this value up to this value of the covering, 0 to 8 atoms. We perform the NIP of one step only, the formatted that one. So observe the platinum, higher activation energy and lower activation energy, and few using NIB and Klein imaging as well, and fewer steps for this part. All of this is well discussed using Professor Kolb, Professor Norskov and Kolb as well. It was a pleasure to have Professor Dennis Jackman, who made the computation for Bernard Feringa, the Nobel Prize in 2006 for molecular machine. But what about molecular machine with this talk? Because molecular machine, you need to use TD-DFT. So Professor Dennis Jackman stayed with us almost 15 days just working with TD-DFT, because if you put some dye on the semiconductor, we need to study how this species, the UV band and the band gap of this dye of this species. So we perform a benchmark of 41 organic molecule, 36 exchange condition, the hybrid TD-DFT. We compare that one with 9 wave function theory, CC, couple cluster, and for that we're using Gaussian 09 for that one. And we compare here, we can see almost bit relief and Coulomb attenuated bit relief, 12 and 9. It's quite similar to couple clusters, singlet, doublet, like that one. So a good accuracy. Even when we have long correlated or WB197, like the one when we have van der Waals and Grimm's currency, this part on the Hamiltonian, it's good result compared to bit relief. And for sure, lower compared to couple cluster CC3, but almost the same result of CCSD and this part. As a major conclusion, I would like to say that transmission lines are a powerful tool, isn't it? Not to obtain the charge transfer double layer, but the alpha value as well, the transport, resistance, the trapping, the capacitance of trapping, using single, double, triple lines model. Heat field science, on material science, we can use rich refinement to obtain structural parameter, crystal size, LETC, using Mark Dolez's preferential. Using computational chemistry, we can obtain dose, p-dose, band structure, charge density, the effective mass of electron hole, the band center, using NIB. and use TD-DFT to study dye injection on the semiconductor especially for the division one, isn't it? Especially using push-pull dyes as well. And now we are focused on machine learning, especially neural network as well, for the polyaniline and the exciton transfer or polaron and bipolaron flux along the channel of aniline. So here in Mato Grosso is this way. Professor drink a cup of coffee and students have a very typical kind of drink called tereré. So it's the Cynthia who performed the TD-DFT, Leonardo and Ricardo performed platinum. Leonardo now is in UFSCar with Professor Alejandro. Platinum and the Band Center computation. Erickson performed titanium oxide computation, is performed doctorate in Federal Amazonas University. Marcos and Adriele performed some neural network and machine learning using studying focus on polyaniline. And Gabriel, it's 4 years with our group, so he worked since from QuantExpression to TD-DFT as well, and only this part of machine learning, not yet. And thank you all, guys. And I would like to thank you, CINE, all the committee organizers, Professor Ana Flávia and Rubens from Unicamp, Professor Hudson, Gustavo, Professor Leonardo from Unicamp, Federal, Jequitinhonha and Mucuri to join me in the group and fruitful discussion and brainstorms. Professor Dennis Jackman from Nantes University for TD-DFT computations, and Professor Christensen, because we are changing a little bit of emails, because from Platinum, all these computations is single crystal, isn't it? We need to construct a supercell and a slab on a plane, AKL, milli-indices, isn't it? But the electrochemistry is a polycrystalline. So we're looking for some electrochemistry group who have some electrochemical data with a single crystal, so we can correct this asymmetry of perform computation on only one plane from the groups from platinum from polycrystalline. And thank you very much.
Renato, thank you very much for a very nice talk. Which was a pleasure to heard all this kind of very good arguments about transmission line and how important is to use this. And we sorry to ask you to go to conclusion because most of the participants there's another things to attend, and I'm sorry about this. But thank you very much, very helpful. And there's 2 questions here, and I don't know if we have time for this, but
may I stop sharing just to see the guys here?
Say again?
May I stop sharing or continue sharing?
Yeah. I think so. Rafael Nagal asked you how can you encourage the students to go in this very hard topic to understand, because you know that's this transmission line, this impedance data is extremely hard to understand at the beginning. No, I know you are far beyond on this, but yeah, for the students to start, it's very hard. And what's your thought about this?
Hi, Nagal, it's a very good question, because indeed the transmission line is a lot of equations and differential equations, especially for us chemistry. We are not electrical engineers, and even physics, we need to study a lot of the part of electricity. But as soon as you go to transmission line and we see the future and how deep and keen we obtain the more specific parameters compared to equivalent circuit, you became fall in love. So you cannot come back. Even if you have a high activation energy to transpass with mathematical, or even how to use the programs using routines in MATLAB, ZView, or Sigma plot. As soon as you obtain the structural and electronic parameters, see how is described much better the electronic properties for capacitance, for you can work whatever the group of semiconductors, group of stored energy, group of polymers, group of full cell device, it doesn't matter. If you know that, you can work with a lot of people and you just became fall in love. The mathematical part is quite harder really, but as soon as you start with Euler, you just stop with Biscuit.
Thank you very much for clarifying this. Rubens also would like to thank you about the nice presentation, and ask you if you can comment on the impact on the definition of the control of volume to carry out the simulation when and you want to explore the specific phenomenon. I guess the idea is to ask if there is an issue with the porals, but is there any issue with the volume of the porals itself?
The volume.
Yeah.
Yeah, the volume of the pores it's considered by Kaiser. Kaiser was the first to pay attention to the one. During the first model, the pore was only cylindrical. It's a pipeline. It's a quite hard simplification, isn't it? It's a pipeline as a tube. As we know, we have tube if this way, we have tube in this way, we have this morphology of tube, and all these parameters are related or the middle in frequency, middle frequency. Higher frequency, we have 45 degrees, so we have a transmission line. Lower frequency, we have warp or charge transfer resistance. The middle frequency will give us the clue for what kind of the pores we have the one. Indeed, we would like to perform some BET, Braun-Nemmer-Teller computation, and perform some BET. I didn't see yet. It's a clue for the guys, a brainstorm, perform a BET, have some brainstorm, some insight of the pore morphology, and implement that one on the transmission line equation. But all the information of the pore morphology, the volume and the morphology itself is in the middle values of frequency. It's considered as well. It's taken account.
I guess one last question just to finish about the TLM. Pablo asked you, I wonder how researchers deal with the problem that as we want to build a more realistic model, we get more complex equations with more parameters. Then more parameters appear and more successful combination of parameters can give you the same quality of fitting.
That's the very wonderful question. It's the first, indeed, it's the first page of the Triboulet, the Triboulet impedance book, because it's a very famous quote in Indian. A blind guy touched the elephant and say, oh, it's a sphere. Another guy touched the head of the elephant, no, say it's not a sphere, it's a tube. And the other touched the tail and said, no, it's a flower. And it depends on the part of the touch on the elephant, you say something, it's a sphere, it's a flower, or it's a tube. So you can use the Okan razor blade, isn't it? The most common, the people use the Okan razor blade. So when I did couple of short courses with Professor Gabrieli, Professor Triboulet, and I've made some courses with Professor Lasha as well. And the best, we every time discuss this one, and we use the easier model, isn't it? Because we have a very complex equation. If you put everything together and put the mixer twice, you fit everything, isn't it? But if you have the transform, the T is student and the F is student related to the statistical parameter, we have some equations, statistical parameters from the fit to obtain the best values. If we have two transmission lines who fits pretty well, which ones fit pretty well the same model, and we obtain the statistical parameter to implement on this equation and say, no, guys, although this transmission line makes sense and this one made sense as well, and we have 4 nines plus after the comma, this one is better because the statistical parameter makes sense and it makes sense the physical chemistry parameter as well.
If it's simpler, it's better.
If it's simpler, it's better. And if you have a statistical parameter, chi-square, F distribution, T students distribution, you have some to prove why you're choosing that one.
We would like to thank you once again very much to find the time to be here today with us. And we met next time tomorrow, guys. And you guys going to receive an email 1 hour before the event with the new link to join us tomorrow. Tomorrow will be the whole day. So today is only in the morning. I'd like to thank you, everybody, for attending, to be here, and Professor Ana, Rubens, Gustavo, Lucia, Renato, Laurence, and all the guys, Cristiane, the Super Secretary, and everybody that attended today.
Thank you. Thank you very much indeed.
Congratulations for the talk. Congratulations for the organization. Woodson, Mary, Lucia, Gustavo, and all the students, all the participants. Very good.
Thank you to all. See you tomorrow.
See you
Thank you,
tomorrow.
everyone.
Tomorrow morning. Bye.